The formal system of the predicate calculus, which includes predicate symbols, a theory of functions, and quantified variables, was intended to be a language for describing mathematics and its philosophical foundations. It also plays a fundamental role in creating a theory of representation for artificial intelligence. The first-order predicate calculus offers the tools necessary for automating reasoning. A language for expressions, a theory for assumptions related to the meaning of expressions, and a logically sound calculus for inferring new true expressions. Whitehead and Russell's 1950 work is particularly important to the foundations of AI, in that their stated goal was to derive the whole of mathematics through formal operations on a collection of axioms. Although many mathematical systems have been constructed from basic axioms, what is interesting is Russell and Whitehead's commitment to mathematics as a purely formal system. This meant that axioms and theorems would be treated solely as the strings of characters. Proofs would proceed solely through the application of well-defined rules for manipulating these strings. There would be no reliance on intuition or the meaning of theorems as a basis for proofs. Every step of a proof followed from the strict application of formal synthetic rules to either axioms or previously proven theorems, even where traditional proofs might regard such a step as obvious. What meaning the theorems and axioms of the system might have in relation to the world would be independent of their logical derivations. This treatment of mathematical reasoning in purely formal and hence mechanical terms provided an essential basis for its automation on physical computers. The logical syntax and formal rules of inference developed by Russell and Whitehead are still a basis for automatic theorem-proving systems, presented later, as well as for the theoretical foundations of artificial intelligence. Alfred Tarski is another mathematician whose work is essential to the foundations of AI. Tarski created a theorem of reference, wherein the well-formed formula of Frege, or Russell and Whitehead, can be said to refer, in a precise fashion, to the physical world. This insight underlies most theories of formal semantics. In his paper, The Semantic Conception of Truth and the Foundation of Semantics, Tarski describes his theory of reference and truth-value relationships. Modern computer scientists, especially Scott, Strachey, Russell, and Polkin, have related this theory to programming languages and other specifications for computing. Although in the 18th, 19th, and early 20th centuries, the formalization of science and mathematics created the intellectual prerequisite for the study of artificial intelligence, it was not until the 20th century and the introduction of the digital computer that AI became a available scientific discipline. By the end of the 1940s, electronic digital computers had demonstrated their potential to provide the memory and processing power required by intelligent programs. It was now possible to implement formal reasoning systems on a computer and empirically test their sufficiency for exhibiting intelligence. An essential component of the science of artificial intelligence is this commitment to digital computers as the vehicle of choice for creating and testing theories of intelligence. Digital computers are not merely a vehicle for testing theories of intelligence. Their architecture also suggests a specific paradigm for such theories. Intelligence is a form of information processing. The notion of search as a problem-solving methodology, for example, owes more to the sequential nature of computer operation than it does to any biological model of intelligence. Most AI programs represent knowledge in some formal language that is then manipulated by algorithms, honoring the separation of data and program fundamental to the von Neumann style of computing. Formal logic has emerged as an important representational tool for AI research, just as graph theory plays an indispensable role in the analysis of problem spaces, as well as providing a basis for semantic networks and similar models of semantic meaning. These techniques and formalisms are discussed in detail throughout the body of this course. We mention them here to emphasize the symbolic relationship between the digital computer and the theoretical underpinnings of artificial intelligence. We often forget that the tools we create for our own purposes tend to shape our conception of the world through their structure and limitations. Although seemingly restrictive, this interaction is an essential aspect of the evolution of human knowledge. A tool, and scientific theories are ultimately only tools, is developed to solve a particular problem. As it is used and refined, the tool itself seems to suggest other applications, leading to new questions and ultimately to the development of new tools.